All right, there we go. Okay, so thanks everyone for joining. Today we're very happy to have Pratik Rath, all the way from Berkeley, who's going to tell us about holographic Renyi entropy from quantum error correction. So Pratik, thank you very much. Sorry for the delay, and the floor is yours.
All right. Thank you so much. Thank you so much for inviting me for this talk. It's pretty early here in Berkeley. It's 7 a.m. here, but I'm glad to tell you about my work. But just in case I'm sloppy with it, please do ask questions so that you get a fair idea of what I did. So this work is essentially based on this paper I published last November with Chris Akers, my collaborator here at Berkeley. And also very closely related ideas were discussed in this other paper by Shi Dong, Daniel Harlow, and Don Marolf. So we coordinated the release of these papers. So similar ideas are discussed there as well. So please look at both papers. All right. So with that, let me get started by just giving you a preview of what I'm going to be telling you about. And the thrust of this talk is going to be that the holographic prescription for computing Renyi entropies can be explained completely by using just the formalism of operator-algebra quantum error correction as a tool to understand ADS-CFT. So quantum error correction in general has given us a lot of good understanding of the ADS-CFT dictionary. And in particular, what I'm going to tell you about is that the prescription for getting Renyi entropies can also be explained in a similar fashion. This, in fact, is slightly more constraining than any of the previous results because it imposes more constraints on the error correcting code. So it's not a very general code. There are particular constraints you need to place on the code. And so it refines our understanding of holography. So that's going to be the general idea. Okay, so with that, let me come to the overview of the talk. So initially, I'm just going to talk about the connection between holography and quantum error correction as we've had it till now. Then I'll briefly review the formalism of operator-algebra quantum error correction, or OQEC as I'll call it henceforth. And then I'll remind you about what Renyi entropy was and how you calculate Renyi entropies in ADS-CFT, and then compare that to the calculation in OQEC. And we'll be able to see some kind of a connection between these two. Eventually, I'll talk about implications for tensor networks. And finally, I'll summarize and talk about some future directions. Okay. So let me start with holography and quantum error correction. Just to remind everyone, or just to tell anyone who's not familiar with this, ADS-CFT is this duality between a gravitational theory living in the bulk. So here I've just drawn this toy picture of a cylinder. The inside of the cylinder is where the gravitational theory lives. It's in d+1 dimensions. And there's a non-gravitational quantum field theory which lives on the boundary of the cylinder, which is in d dimensions. And since we don't understand quantum gravity very well, one might want to ask all sorts of questions about quantum gravity. And because you have this duality, you might be able to answer all of these questions just by asking questions in field theory, which we understand pretty well. The only issue is we need to understand the dictionary well enough to ask the right questions. And so the key focus of this talk is going to be to understand this dictionary better. And a large part of the dictionary, so in the past decade, there's been a lot of progress that's come from thinking of holography as a quantum error correcting code. So quantum error correcting codes were studied in quantum information for a long time, but surprisingly had a lot of applications to understanding holography. And so I'm going to use that formalism to explain one more such entry into the dictionary. All right. So here I've just drawn one particular time slice of the cylinder I showed you before, where I've split the boundary into two subregions, capital A and capital A bar. And one of the most important dictionary entries that we learned of around 2006 was the Ryu-Takayanagi formula. So the Ryu-Takayanagi formula gives a prescription to compute the entanglement entropy of this boundary subregion capital A. So if you take the density matrix of the boundary theory, the state on the boundary theory, and trace out the remaining portion, capital A bar, compute minus trace rho log rho. That's the von Neumann entropy on the boundary. And the holographic dual to this is pretty simple. It's just given by the area of the extremal surface. In this case, we're talking just about time independent states. So we just think about minimal surfaces, which lie on this time slice and are anchored to the endpoints of the boundary of A. So here you can see this surface gamma of A is anchored to the endpoints of the subregion capital A. And then people came, and so Faulkner, Lukowitz, and Maldacena added corrections to this thing. So the leading term from the Ryu-Takayanagi formula is an order 1 over G term. So that's the leading term in the limit where G goes to 0. The next order 1 correction comes from the bulk entropy, which is the bulk entropy of the matter fields that live within this subregion of the bulk little a. So little a is this slice that runs between gamma of A and the boundary region A. And in particular, its domain of dependence is what we call the entanglement wedge. So the entropy of the bulk fields in the entanglement wedge is the order 1 correction. This formula has been refined further, and there's a better prescription to compute this thing, which is called quantum extremal surfaces. But the error correction can not accommodate all of that, and I'll probably talk about this when we get there. But I'm just going to be talking about the RT plus FLM corrections at this order. So the boundary theory, so the key idea was that came from Almeri, Dong, and Harlow, was that the boundary theory encodes the semi-classical bulk effective theory as a quantum error correcting code. So the duality tells you that there's an isomorphism between the boundary Hilbert space and the bulk Hilbert space. So in principle, there's one state on each side. So it's a bijection. But if you look at the low energy states in the bulk, which have some semi-classical description, they're a much smaller set of states, and they are encoded in a larger Hilbert space, which is the CFT Hilbert space, as a quantum error correcting code. So a quantum error correcting code has this feature where it redundantly encodes a lot of information. So in particular, some portion of the bulk could be accessed by multiple boundary regions. And the way it does that is through this formalism of quantum error correction. In particular, understanding holography as a quantum error correcting code led to a proof of what's called entanglement wedge reconstruction. So entanglement wedge reconstruction is the theorem that all the bulk observables within, say here, the blue region marked little a, can be reconstructed by operators which have support only within the boundary region A, capital A. And similarly, operators within A bar, little a bar, can be reconstructed purely with support on capital A bar. So this explains how, in some way, how the degrees of freedom are encoded spatially. So with this background, I'd like to start by giving you a review of the formalism of quantum error correction, and in particular, operator-algebra quantum error correction, which is the most general form that we understand till now. Okay, so operator-algebra quantum error correction can be described with three.
Pratik,
Yeah.
I have a question.
Yes.
And the question is it obvious that the error correction, so like information is stored in, how to say, like that the information represented by semi-classical gravity state is stored as a quantum error correcting code in the like full Hilbert space, or it's also possible that there's some, you know, like auxiliary construct, and it is this auxiliary, you know, space for which quantum error correction occurs.
Do you mean,
well, you said that there's an isomorphism between Hilbert space in the bulk and Hilbert space on the boundary,
Yes.
then we know that not every state represented by a semi-classical geometry.
Yes.
Sorry, the other way around. Semi-classical geometries just form like some corner of a much bigger Hilbert space, right? So is it obvious that this quantum error correction occurs in this larger Hilbert space, or is it possible that there's something more to it, some additional structure?
Well, right now I'm just making the claim that, so right now I'm just making the claim that within the whole Hilbert space, so even if I forget about the boundary Hilbert space, even if I just think about the full quantum gravity Hilbert space, the low energy effective theory is some subspace of that larger Hilbert space. And then I guess you're asking, my claim is that this little Hilbert space is encoded purely in the CFT without any auxiliary degrees of freedom.
I guess so, yeah.
I would say so. Do you think there's an issue with that? Like, it's not clear, maybe subtleties with black holes, I'm not sure, but I think the belief is that that is true.
Okay, thanks.
Yes. I mean, that's what I'm going to go with. So there is a smaller Hilbert space which describes bulk effective field theory, and that is encoded as a code subspace in the full CFT without any other degrees of freedom. Okay. All right. So operator-algebra quantum error correction. So the ingredients that we need for this is three things. So there's a physical Hilbert space, which you should think of as the CFT Hilbert space, which factorizes as HA tensor HA bar. Then there's a logical code subspace. So H code is the subset of the total Hilbert space of the CFT. And this you should think of as it's isomorphic to the Hilbert space, which describes semi-classical low energy effective field theory in the bulk. And
one of the factors, or does this also factorize over? Is the code subspace like isomorphic to HA? Is one of the tensor products, or it also splits over the
it'll have a different decomposition. I'll get to that.
Okay.
Yeah. There's a von Neumann algebra M, which you should think of as the set of bulk effective field theory operators. So operators that preserve the code subspace. So operators that don't take you out of low energy effective field theory, which act on this Hilbert space H code. So given any von Neumann algebra M, there's a preferred decomposition to H code such that it factorizes in the following way, and this probably connects to your question, where H code has this decomposition where it's a direct sum over this index alpha, which I'll call the alpha block. So it has this block decomposition where within each block it factorizes as H a sub alpha times H a bar sub alpha. So H little a sub alpha is sort of the degrees of freedom which are within, in this figure, the blue region little a. So it's the entanglement wedge, and the complementary one is in the complementary wedge. So it's not exactly a factor, but it's a direct sum of factors. So this decomposition is such that all the operators within the von Neumann algebra M act in the following way. So they're non-trivial on the first factor and its identity on the second factor within each block. So it's a direct sum of such operators. Similarly, M prime, which is the commutant of M. So the commutant of M is the set of all operators that commutes with all the operators in M, is similarly given by the identity on the first factor and a non-trivial operator acting on the second factor. And so direct sum of those. And the center is something that commutes with both. So the center is something that is contained in M and in M prime. And these are basically all the operators that look like the identity within each block. So they commute with each of O tilde M and O tilde M prime, but they can have non-trivial weights on each of the blocks. So some number for each block. Okay. All right. So with that, one can decompose the Hilbert space of the boundary subregion capital A in the following way. So HA can be factorized. So here I'm just working in finite dimensions, by the way. So I'm never going to be talking about infinite dimensional Hilbert spaces. These are all finite dimensional Hilbert spaces. And we can talk more about what happens when you talk about infinite dimensions. So finite dimensions, all I'm doing is just decomposing HA in the following way. It's just some factor A1 times A2 plus some remainder A3. So I'm just factorizing, dividing HA in an appropriate fashion so that the dimension of HA1 alpha is the same as this first factor HA alpha, which featured in the code subspace. I'm just trying to take out a factor from the Hilbert space of the subregion A, which will be able to encode the degrees of freedom that lie in the entanglement wedge. And then these remaining pieces will sort of be the redundant pieces. So having set up that, the OQEC with complementary recovery is defined by requiring that all the operators in the von Neumann algebra M can be encoded within the subregion A for all states in H code. So if you pick any state in H code, there exists, so suppose you take an operator OM tilde, which is in the von Neumann algebra M, there exists an operator in purely restricted to the subregion capital A, which acts on psi tilde in precisely the same way. So it has all of the same matrix elements. But this is only within the H code. And similarly, the same is true for the Hermitian conjugate. And by requiring an OQEC with complementary recovery, I'm requiring that the same is true for M prime. So similarly, operators in the complementary entanglement wedge can be encoded entirely on the subregion A bar. This is precisely the reason that we're working only to order 1, because in ADS-CFT, the actual prescription for computing entanglement entropy on the boundary actually corresponds to this quantum extremal surfaces prescription, if you're familiar with that. And that moves the surface. So here the surface gamma of A is fixed when you're talking about corrections to order 1, but it can move when you're talking about corrections to higher orders in G Newton. And so that is something that I currently don't know how to include in this picture. So right now we're just talking about corrections until order 1. All right. So equivalently, so requiring that all of the states in the code subspace can be such that the von Neumann algebra M or M prime can be encoded on the boundary regions A and A bar is equivalent to requiring that any state in the code subspace can be written in the following way. So this is a particular basis that we're looking at. So alpha is represents the block number, and I and J represent the indices corresponding to the entanglement wedge code subspace index A and A bar. And this is a particular basis for the code subspace. So any state in the code subspace is a superposition over such states. So if I just give you a prescription for how to encode these states, that's sufficient. And the way it will be encoded is that there are unitaries which acts on purely on the subregion A and purely on the subregion A bar, which essentially make it look in the like the following. So there's a state alpha I, which is now encoded on the boundary factor A1 alpha. So we're looking at this particular decomposition where HA is a direct sum over alpha of HA1 tensor HA2. So this A1 is used to sort of encode or decode the information in the alpha I piece. Similarly, A1 bar is used to decode the information on alpha J. And then A2 is sort of a redundant piece. So this is what we call the chi state, which is just used to redundantly encode this information. These two are equivalent ways. And so I'll just be starting from this and using this particular state. Okay, So this condition clearly ensures that the von Neumann algebra M is now robust to erasure of the subregion A bar, because if you traced out over A bar in this equation, you would lose the A bar pieces here, but you still retain all of the information of this alpha I. And so anything that you could have accessed within the entanglement wedge can now be accessed from purely the subregion A. You don't need any of the information of A bar to access all of that information. Okay. So once we just take this state, so a general state in the code subspace would be superposition over such basis elements. You can take the state and then look at a general density matrix, trace out over the portion A bar, and finally what you land up with is a state of the following form. So a general state rho A tilde, the reduced density matrix on the subregion A on the boundary, looks like it's conjugated by these unitaries A and UA and UA dagger. And it's a direct sum over alpha of some state rho alpha, which was which sort of corresponds to the degrees of freedom within the code subspace. So those are the low energy degrees of freedom, and a state chi alpha, which came from the redundant piece chi alpha in the state. And these p alphas, so these are normalized, so that trace of rho alpha is 1 and trace of chi alpha is 1. So these p alphas represent the weighting of each of the blocks. Okay, so you can have some different weighting, and there's some state within each block. Now, if you just take this state and try to compute its von Neumann entropy, what you get is the following. So after simplifying it, you can make it look like these three terms. So there's a trace of rho tilde LA, where LA is this area operator defined by a direct sum over alpha of S of chi alpha. So it's the entropy of this chi alpha state with an identity on each block. So in particular, this is an element of the center of the von Neumann algebra M, because it's identity on each block, but it's some number multiplied within each block. And it's non-trivial, because within each alpha block, you could have a different chi state. And so S of chi alpha could take varying values. And so the area operator is this non-trivial operator. So the first piece is the expectation value of this area operator in the code subspace state. Then there's this Shannon entropy terms, which sort of corresponds to the classical entropy of having this mixed state. And then there's this extra term, which comes from the bulk entropy. So rho sub alpha were the code subspace, was the portion which was corresponding to the low energy degrees of freedom. So this is the entropy of the low energy degrees of freedom. So this is very analogous to the RT plus FLM formula. So this you should think of as the area piece, and this is the bulk piece. And this mixing term comes from if you mix two very different geometries. So this was exactly what was expected in ADS CFT. So Harlow argued that Ryu-Takayanagi formula is really a feature of general operator algebra quantum error correcting codes. And that's why it makes sense that ADS CFT is this. Yes?
I have a question online. So actually, I don't understand the middle term.
Yes.
Would it arise if we start with a mixed state, or because you mentioned something about superposing? That's not something that is super easy to do, right? And like we don't know anything like this.
Yeah, we don't. But so there is this paper by Almeri, Dong, and Harlow. Almeri, Dong, and Swingle, which sort of talks about this. So you can think about the duals to. So suppose you in the bulk you wanted to consider something like superposition of a black hole of one temperature with another temperature or something. When you reduce it to a subregion that's small enough, what you see, so you can do this calculation in some kind of approximation, and you see that there is this extra term which shows up at order 1, which comes from this mixing term of two different geometries. So usually we ignore this piece because we're usually working around one background. So we always just see the RT plus FLM term. But if you were to think about a more generalized form of this, then you would have to include the Shannon entropy term as well.
Okay, thanks. And I will look into this paper. A second question is, I always thought that Ryu-Takayanagi plus FLN is an approximation. I mean, to the leading order in say 1 over n, right?
Yes. Yes.
And where this, I mean, since it's an approximation in the bulk, like if your result that uses quantum mechanical things is exact, then it's a bit weird, right? Because it would suggest that maybe like FLM plus RT is exact. So is there some tension there, or is okay?
That's a good question. So actually, all it's saying is that ADS CFT does not work as an exact quantum error correcting code with complementary recovery, as we know, because the quantum extremal surfaces tell us that the gamma of a surface can move at subleading orders. So I think it's an issue of trying to understand ADS CFT as an exact quantum error correcting code. So there might be that might be the issue.
So to rephrase it, you're saying that RT plus FLN like agrees with the exact quantum error correcting code, and you're saying that if you were to go to subleading orders, so like 1 over the central charge squared, or like 1 over n, whatever power,
yes,
then it's not going to work that nicely.
Yes, I mean, so if you take any operator quantum error, or any OQEC with complementary recovery, the RT plus FLM is exact, but in ADS CFT it's not. So in OQEC, we need to modify OQEC with complementary recovery in some way to recover the quantum extremal surfaces prescription. Does that answer your question? Okay. Okay, so let me move on. Is there a question? Sorry, is there a question?
There's a microphone turned on. And, oh yeah, it's
Okay. All right. So here in this case, we are including many different alpha blocks where there's S of chi alpha could take very different values, and LA you should think of as A over 4 G Newton. So the area of the extremal surface or the minimal surface takes on very different values. So in some sense, we're including very different geometries. And this is really motivated by this paper that I was talking about by Almeri, Dong, and Swingle, where they talk about the possibility of doing this, and the Ryu-Takayanagi plus FLM formula still working. Okay. I just wanted to give you some quick intuition for this state from lattice gauge theory. In a gauge theory, if you just forget about the boundary and just think about the bulk, there are gauge constraints, and so the Hilbert space of any subregion naively doesn't factorize. So if in this bulk picture, if you just consider some subregion little a and little a bar, there's some entangling surface that cuts across. In a lattice gauge theory, the links sort of contain these degrees of freedom, right, which corresponds to the gauge field. And so there's no way to directly decompose the Hilbert space as a factor. So what has been prescribed and by a few people is that what one needs to add these edge modes at the entangling surface, which are marked by these white dots, which sort of allow you to factorize the Hilbert space. There are these extra degrees of freedom you need to include. So you think about an extended phase space, and then think about states within that space which satisfy all the gauge constraints. So this is very analogous to what we have here. So chi alpha you should really think about as these extra degrees of freedom that you include which are localized in some sense to the entangling surface, and then rho is sort of the state of the low energy degrees of freedom which live in the subregion A. P alpha then you should think of as sort of the weighting of these different superselection sectors. So for example, if you were in U1, then you could measure the electric field. And so different values of the electric field would correspond to different superselection sectors. It's a classically measurable observable. And so two different values of the electric field would sort of decouple into different blocks. And so that's sort of the analogy I want to make. But in particular, people have also thought about this a little more in the context of ADS CFT. So for example, Jennifer Lin has made the proposal that the Ryu-Takayanagi formula should be explainable in terms of these chi state. So the chi degrees of freedom should account for all of the RT entropy. And that's sort of what I want to motivate further. There's an important constraint that comes from lattice gauge theory, which is that these chi alpha degrees of freedom, in order to satisfy the gauge constraints, require chi alpha to be maximally mixed. This is something that was not required in the OQEC as of now. And somehow matching on to the Renyi entropy prescription will actually lead us to this conclusion. So there's a strong connection between these two things. Okay. All right. So with that, let me move on to the main result that we have, which is about the Renyi entropy. So the Renyi entropy, just to remind you, is a one-parameter generalization of the von Neumann entropy, which is defined in the following way. So it's 1 over 1 minus n times log of trace rho to the n. And it doesn't have a simple holographic prescription similar to the RT formula. So the RT formula is quite a simple thing where you just compute this geometric quantity. The von Neumann entropy, the Renyi entropy doesn't seem to have, or maybe is in fact is known to not have a simple description in the same way. However, there's a close cousin, which is called the refined Renyi entropy, which is, I'll call as n tilde, which is defined in the following way. So it's n squared times the derivative of n minus 1 over n times the Renyi entropy. So it's some other quantity which is closely related to the Renyi entropy. And this, in fact, does have a generalization to the RT formula, as was shown by Shidong. So the refined Renyi entropy is actually a more natural one-parameter generalization in the context of holography. And one way to see that is the following identity. So you can just take any arbitrary state rho, try to compute the refined Renyi entropy as n tilde, and it's actually equal to the von Neumann entropy of a different state. So this rho n is just rho to the n normalized. So if you just take rho to the n normalized, compute its von Neumann entropy, that's the same as computing the refined Renyi entropy of the state. So since there's this connection between the refined Renyi entropy of one state and the von Neumann entropy of a different state, it seems natural that the von Neumann entropy satisfying an RT plus FLM formula should naturally also correspond to some kind of RT plus FLM like formula for the refined Renyi entropy as well. And we'll see how that works. And notably, both of these one parameter generalizations approach the von Neumann entropy in the limit n goes to 1. So in the quantum information community, the Renyi entropy has been studied much more. It was always thought of as the natural generalization. However, in the context of holography, it seems like this refined Renyi entropy is the more natural quantity. And in fact, this hasn't been very well studied. So we don't know a lot of properties about Sn tilde. So that's one thing to look at more carefully. Anyway, so let me talk about how we calculate Renyi entropies in ADS CFT. So in ADS CFT, the Renyi entropies can be calculated by, so what you need to compute is this trace log of trace rho to the n. So you need to compute the density matrix to the nth power. So the standard way to compute this is the replica trick. So you start with n copies of the boundary CFT, and then we can compare to the bulk dual. Now, Shidong did all of this analysis, and effectively, so at the leading order, what it ends up being is just the following prescription. You just shift your bulk action by the following. So you just shift it to n times the bulk action that you started with, plus this extra term, which is n minus 1 times the area of a Brane. So this is sort of the natural Brane action with an appropriate tension. So here it's n minus 1 over 4g Newton is the coefficient that shows up in front of it. And now if you do the path integral with this new action, so n I bulk plus n minus 1 a Brane over 4g Newton, that gives you a new holographic dual where, so initially you start off with some geometry which was say smooth, and now it's a new modified geometry which has this added Brane with appropriate tension n minus 1 over 4 n g Newton, which is also anchored to the entangling surface partial A. Okay, so it's anchored to the endpoints of A, but it has a non-zero tension, and so it back reacts on the geometry, changing the geometry, and In particular, the way a brane changes the geometry is it generates this conical deficit, which is proportional to its tension. Okay, so
Pratik,
yes.
This extra term that you add, this is basically like a Gibbons-Hawking boundary term that gets added to the action. Think of this.
I wouldn't think of it as a Gibbons-Hawking term. This is more like,
well, just by analogy with the this proof by Lukowitz and Maldacena, where they where they derive RT with a similar reference.
I see what you're saying.
The thing that gives you the conical deficit in the bulk is basically arises from this kind of term as well.
I see what you're saying.
I'm just curious.
Yes, it's derived by the same trick for sure. Yes, but there they, I think, just use it as an auxiliary trick. I mean, so yeah, but I guess you can say the same thing. Yes, I think you're right. Yes. So in that case, like they're looking at the limit where n goes to 1, and so this brane is sort of close to tensionless, and just computing this Gibbons-Hawking term is what gives you this. Yeah. So in this case, you should think of this as some independent brane that you're adding to this geometry, and that back reacts on this geometry. Okay, so given all of this setup, so now that you have this new back-reacted geometry, the cosmic brane prescription, as prescribed by Xidong, is that the refined Renyi entropy of the boundary subregion A is given by the area of this brane divided by 4g Newton, plus some bulk corrections that come from the entanglement wedge, little a, which is also the Sn tilde, so the refined Renyi entropy of the bulk state. So the saddle point solution here, which we found by shifting the bulk action by this particular prescription, is it satisfies the Einstein equations everywhere, which comes from the saddle point equation for the metric. And in addition, the equations of motion for the brane ensure that it's extremal. So in this new geometry, the RT surface is the brane, for example.
Pratik, one question.
Yes?
Was this formula proved by Xidong?
What Xidong proved was this first part, where it was A brane over 4g Newton. And he just made a comment about how the next order terms could be included. This was actually then further developed by Xidong and Lukowitz in their paper where they talk about quantum extremal surfaces. So a similar formula appears there. But there appear to be subtleties with the boundary conditions on gravitons. And so there is still some controversy about what should be done with the order 1 piece. But roughly, the expectation is that this is true. But there are still some subtleties with gravitons. Up to that, modulo that subtlety, it has been proved.
Okay.
Yeah. It's essentially the same kind of proof. So, I mean, it's essentially just like the FLM proof. It's very similar. Okay. So, again, from here, we clearly see that in the limit n goes to 1, we recover the RT formula, RT plus FLM formula, because the brane becomes tensionless. So, this A just satisfies extremality and doesn't back react on the geometry. So, it's just A over 4g Newton of a minimal surface in the original geometry, plus the bulk corrections. And so the question was, can we see this directly from the quantum error correcting picture? And so I'm trying to motivate how we would see that. Okay. So in OQEC, it's pretty straightforward to compute the Renyi entropy. We saw earlier that general reduced density matrix on the subregion A takes the following form. It's a direct sum over alpha of this P alpha times rho alpha tensor chi alpha. So if we compute the refined Renyi entropy of the state, it again picks up these 3 terms, where the 3 terms come basically from the P alpha piece, the rho alpha piece, and chi alpha piece. The chi alpha piece takes this form where it's a sum over alpha of this P alpha n. So P alpha n is a new probability distribution, which is essentially like the nth power. So it's like P alpha to the n, trace chi to the n, trace of rho to the n, normalized. So it's a new probability distribution. So it's the weighted sum with this probability distribution of the refined Renyi entropy of chi alpha plus this Shannon term and plus this bulk term, which also shows up with this refined Renyi entropy. So now this, earlier we made a connection of this first term to the area piece, this was the Shannon piece, and this was the bulk piece. But right now, even though this sort of resembles that, it's still not in the appropriate form that we make a connection to that. So there's still some conditions we need to impose on the code in order to interpret this as the cosmic brane prescription. So notably, this P alpha n you should think of as a new state, or as sort of the weighting of a different state, which is some modified version of the original P alphas. And this will show up later. So in particular, the things that we're going to need to match this, this previous formula here in OQEC to the cosmic brane prescription in gravity is the following. So we first try to understand what the alpha blocks really mean geometrically. And geometrically, we would interpret them as eigenstates of the area operator. So the way we're going to think of geometries is that classical smooth geometries, which are prepared by a path integral, would in general have a support on many alpha blocks, even though they're peaked at a single value of alpha. And each alpha block on its own is not necessarily a smooth geometry that one would think of as a classical geometry. And with this interpretation, we can compute P alpha by using the path integral. And so by imposing that P alpha takes a particular form, which is given by the path integral, and by requiring that the state chi alpha is maximally mixed, namely that all the refined Renyi entropies and Renyi entropies actually equal the von Neumann entropy. If you take any maximally mixed density matrix, all of these things give the answer log D. Okay, so if it's a maximally mixed density matrix of dimension D, all of these take on the value log D. And so the Renyi spectrum of this chi alpha state is actually just flat. And that's going to be one of the key features that we're going to require. So with these three constraints, we'll see that the previous formula that we had here will actually take on the interpretation of a cosmic brane prescription in holography. So after that, we'll be able to write it in this following form, which is what we want. So we'll have the expectation value of the area operator in the state, in a modified state, which we can then interpret as the Brane state, plus this Shannon entropy term, plus the refined Renyi entropy of the bulk fields. And notably, the state rho tilde n, which was, if you remember, the rho to the n normalized, only belongs to the cold subspace if chi alpha is maximally mixed. So just if I get you back here, if you take the nth power of this rho tilde, you would pick up a chi alpha to the n in this piece. And earlier we had defined a general density matrix within OQEC, so state within the code subspace, to basically be an arbitrary state here, but only having chi here. So we would require that the nth power of chi matches essentially chi up to normalization. And that is another way of requiring that chi be maximally mixed. So there's going to be a lot of ways that we'll see that chi is maximally mixed. So one of them is going to be requiring that the term that shows up here is the area operator. Another way is going to be to see that this is the Brane state. And in fact, requiring that the Brane state belong to the code subspace is another way that you can see that chi should be maximally mixed. And I'll discuss all of this at the end. Okay, so let me review the gravitational path integral. Any state, was there a question?
No.
Okay. Okay. So the CFT state is prepared by a path integral. And the bulk dual of this is the Hartle-Hawking wave function. So what one does is, with appropriate boundary conditions described by the CFT path integral, so what I've called J here, there are sources at infinity, and you prescribe some configuration at this yellow time slice, Euclidean time slice, tau equals 0. So there's some G minus phi minus that you prescribe at in the ket, and G plus phi plus that you prescribe on the bra. And with this, the amplitude of this particular state is given by the following. So the density matrix, which is a functional of G minus phi minus, where phi minus I'm using to talk about all of the matter fields, and G plus phi plus, is given by, in the saddle point approximation. So I'm just taking the saddle point approximation in the limit of G Newton goes to 0, is given by e to the minus I bulk over Z with the appropriate boundary conditions. The boundary conditions are essentially of having G minus phi minus, G plus phi plus, and the boundary conditions at infinity. That's the way we compute this density matrix.
So Pratik, so this is
Yes.
going to be the density matrix of a pure state, right?
Yes, this is a pure state, which we prepare on the boundary, and then I'll take a partial trace, and that would make it a mixed state living on the subregion A. Does that answer your question? Yeah. Yeah. Okay, so in order to compute P alpha, so what P alpha meant in the OQEC was that we projected onto a particular value of alpha and then just take the trace. And so since we interpret geometrically the alpha blocks to mean that they are eigenspaces of the area operator, what one does is just fix the value of alpha. So you fix the area here at the extremal surface gamma of A to be the particular value S of chi alpha, and then just perform a trace over this density matrix. So the density matrix was prepared here. You add an extra constraint by projecting onto a given alpha block, and then perform the full trace. Now, this is going to be essentially a very similar path integral. So it has all of the same boundary conditions where with the sources, but it has this extra boundary condition that at this surface gamma of A, it takes on the area given by S of chi alpha, or that's A over 4G Newton. So 4G Newton times S of chi alpha. So that's the way we would compute P alpha through the path integral. And notably, I mean, just from the Hartle-Hawking wave function, one can see that P alpha would have some saddle point solution, but it would also have non-zero value, which is non-perturbatively suppressed with other blocks. So if you, a typical classical geometry that you prepared by this path integral will have non-zero values for all of these P alphas, although only one of them would dominate. So it's very much like a coherent state. So we're trying to think of any classical geometry as a coherent state of, so it's a superposition over different area eigenstates. So each area eigenstate on its own is not very smooth, although the sum is smooth. Okay. So now let us revisit the cosmic Brane prescription. What the cosmic Brane prescription asks us to do is to consider a different distribution where you shifted the bulk action to this n times I bulk plus n minus 1 times A Brane over 4G Newton. So let's just do that. When one does that, so remember that A over 4G Newton, since the Brane always lies on the RT surface, is just the area operator LA, right? So if we just do the same calculation, but now with this modified action, in the saddle point approximation, what I'm going to end up getting is e to the minus n I bulk alpha minus n minus 1 times the area operator LA with the same boundary condition. So this is sort of an important point, that it satisfies precisely the same boundary conditions, which is that the area at the extremal surface is fixed and the boundary sources are identical. So all we require is that Einstein's equations are satisfied everywhere away from the area, away from this surface. And in particular, it can develop an arbitrary conical deficit at gamma of A. And so what you're going to find is that this P alpha n, which is the Brane state, which you obtain by shifting the action, is precisely e to the minus n I bulk of the same saddle. So the saddle doesn't really change. Minus n minus 1 times A Brane with the same boundary conditions. So comparing this with the state we obtained from OQEC, if you remember a while back, this was the state we obtained from OQEC. So if I ignore the order 1 piece for now, I'm just working at leading order in G Newton here. The state looks like e to the minus n I bulk of alpha, because p alpha itself was e to the minus I bulk of alpha. So it's p alpha to the n. So it picks up a factor of n here. And minus n minus 1 times the Renyi entropy of chi alpha. Now, in order for these two to match up, you must need that Sn of chi alpha should be equal to the area operator. The area operator in particular was S of chi alpha, which means that the spectrum of chi alpha, so the Renyi spectrum of chi alpha should be flat. And that is equivalent to saying that chi alpha is maximally mixed. So in particular, from the path integral, we see that requiring that chi alpha is maximally mixed allows us to interpret this new distribution P alpha n as corresponding to what we should think of as a geometry, which is the Brane state that one would use in the cosmic Brane prescription. This is sort of one of the key points. So I'll just pause to see if there are any questions.
So I just have a silly technical point.
Yes.
Yeah, which is your argument for chi alpha to be maximally mixed in your description.
Yes.
You compute the Renyi entropy and you get the power of chi alpha, right?
Yes.
That this has to be equal to chi alpha.
Yes.
So, chi alpha could be a projector onto a pure state.
Oh, yes, sorry. That's a good point. So when I say chi alpha being maximally mixed, the more general statement is that it's a normalized projector. So it could have been, say, identity on a smaller subspace and just normalized appropriately. Then you could think of it as being maximally mixed on that smaller subspace. So I'm just using maximally mixed in loose sense here. The precise statement would be that it's a normalized projector. So in particular, it could have been a projector onto one state as well. That's true. But we know that S of chi alpha is like the area over 4G Newton. So it's certainly non-zero in that sense. So that's why I don't really care about whether it's maximally mixed on this full thing, but it's maximally mixed on that subspace. Yeah, good question. Thanks. Yeah, so let me move on from that. So now what we've seen is that there's many ways that we've seen that chi alpha is maximally mixed. Just to remind you, the area operator was S of chi alpha, and we saw that in the OQEC calculation, what naturally showed up in the same term, which was back here, was this Sn tilde of chi alpha. So in order for this term to be interpreted as the area operator, we already needed that chi alpha be maximally mixed. For rho n to lie within the code subspace, as I discussed earlier, also we required that chi alpha be maximally mixed because we needed the nth power to match up to normalization. For the interpretation of rho n as a Brane state to match up with holography from the calculation that we did in the path integral, also we required that chi alpha be maximally mixed. And in fact, from my earlier discussion about the lattice gauge theory intuition, if ADS-CFT is to be understood in the bulk, so in the bulk, we do have diffeomorphism invariance, so it's also a gauge theory and it has gauge constraints. So the bulk quantum theory does not factorize into subregions little a and little a bar. So naturally, one would think that one has to introduce edge modes and talk about subregions in the bulk. And the prescription and sort of the conjecture by Jennifer Lin was that this is enough to account for all of the Ryu-Takayanagi entropy from the area term. And in particular, that interpretation required that chi alpha be maximally mixed because the formalism of extending the phase space and in gauge theories and then reducing to the gauge invariant subspace naturally gives you this condition of chi alpha being maximally mixed. There's another way in which all of this connects to ADS-CFT, which is that the entanglement wedge reconstruction formula, which was derived by Faulkner and Lukowitz by using modular flow, actually was not derivable before this. So what they actually had used was that what was true earlier was that the bulk modular Hamiltonian plus the area term was equal to the boundary modular Hamiltonian. But what they really required in deriving the formula that they had for reconstruction of operators was that was an exponentiated form of that formula. Now, in particular, if you work through the algebra, you see that the exponentiated form only works if it preserves the code subspace. And it preserves the code subspace only if chi alpha is maximally mixed. So in fact, this is another way to see that chi alpha is maximally mixed. And in fact, this answer it sort of motivates that chi alpha is maximally mixed even to order 1. So the current argument I gave you, we used the saddle point approximation. And because there are these subtleties with gravitons, it's not exactly clear how to show that chi alpha is maximally mixed to order 1. But the fact that we believe in this Faulkner-Lukowitz formula sort of gives an independent argument for why we should believe that chi alpha is maximally mixed to order 1. So with all of this motivation, I make the claim that now we sort of strongly believe that the ADS-CFT code must have this constraint that chi alpha takes the form identity alpha over dim chi alpha. This gives us an improved version of the area operator. So instead of just S of chi alpha, we now know that it's really log dim chi alpha. Okay. So this has a lot of implications for tensor networks. So tensor networks notoriously, so there were a lot of tensor networks. So initially we started with the happy tensor network. So from Harlow, Pastavsky, Preskill, and Yoshida proposed this perfect tensor network to describe holography, where each of the legs was maximally entangled and each of these tensors was a perfect tensor. This explained a lot of features of ADS-CFT. So in particular, how it was working as an error correcting code and the fact that it satisfied a RT formula and so on. But it notoriously suffered from the issue that it had a flat Renyi spectrum. And the same issue is for also a more general version of this, which was the random tensor network. And there was one simple reason for this. The simple reason was that all of these bonds were maximally entangled. So these bonds, these cut bonds is what you should think of as the chi state. And so naturally, all of these states, in fact, did have chi alpha being maximally mixed. So as we saw, chi alpha being maximally mixed leads to a flat Renyi spectrum. And that's the whole reason that no one could ever explain why the tensor networks have a flat Renyi spectrum, but the boundary CFT, of course, does not. It has a non-trivial independence. So with all of the analysis that we have done, it now seems that the tensor network should really be thought of as a single alpha block in this general operator quantum error correction, operator-algebra quantum error correction. And so it's more like an area eigenstate as opposed to a smooth geometry. And a smooth geometry would then be described by a direct sum of these tensor networks, or in some way, if you can introduce a non-trivial center. So there was some work which was done by Don Marolf and collaborators where they talk about a tensor network which has a non-trivial center. That's another way in which you could possibly describe a smooth geometry. So you somehow need to add more degrees of freedom, which gives it a non-trivial center. But there's still a puzzle here. So in all of the calculation that I did when I was talking about OQEC, I just considered a particular factorization. So we just factorized the Hilbert space into these subregions A and A bar, both of which it was just some fixed subregion. However, the tensor network does more than just that. It actually, you could consider this subregion, or you could consider like some other overlapping subregion, and it actually satisfies the RT formula for all of them. And chi alpha is maximally mixed for all of them. So in fact, the tensor network does a bit more than what I just asked it to do, which was that it somehow fixes the areas of all of the RT surfaces, which is somewhat unnatural from the bulk because the area operator doesn't commute. So if you consider another area, minimal cut, say across different bonds, which is anchored to a different subregion, those two areas, those two HRT surfaces would cross. And so commute. So if you fix one of them, there's sort of infinite uncertainty in the other one. So it's still a puzzle as to how the tensor network simultaneously fixes all of these areas and how this should be interpreted within holography. And so this might be something interesting to understand. And this also could be closely related to the reason of why time evolution of tensor networks is still poorly understood. So we don't exactly understand how the time dependent part of this works. And that might be because we're fixing the area. So when you fix the area, you sort of fix the metric, or let's say you fix the metric on the entire slice, because you're fixing the areas for all of these, all of the HRT surfaces. And so fixing the metric would then make the conjugate momentum infinitely uncertain. And so it makes sense that as soon as you try to time evolve, it just evolves into something very unlike what you started with. So these are still things to understand about tensor networks, but at least the Renyi part of it has been explained by what we've done. So with that, let me try to summarize what I've told you today. Essentially, the main result was that this formula of computing the Renyi entropy, or the refined Renyi entropy from OQEC, matches on to the cosmic brane prescription by putting appropriate restrictions on the code, which was that chi alpha be maximally mixed. And so that gives us this new refined version of the area operator, which is a direct sum over alpha of log dim chi alpha. As long as, and the way we should really think about this in the bulk is that each alpha block is an area eigenstate as opposed to a smooth geometry. This also motivates the fact that edge modes are responsible for the area piece, because chi being maximally mixed was naturally motivated by this gauge theory construction. And so that is something to be understood better. Higher orders in G Newton still need to be understood properly. So here, the OQEC calculation shows that there is this refined Renyi entropy term coming from this. And there are still these subtleties with gravitons that need to be worked on to really understand what happens at order 1. At higher orders, it's even worse, because the OQEC formalism, as was pointed out, is not even sufficient to talk about complementary recovery. So we need to somehow include the fact that the HRT surface moves at higher orders into the formalism in order to understand higher orders in G Newton. And throughout this talk, I was working purely in finite dimensional Hilbert spaces, but there might be effects from infinite dimensional Hilbert spaces which affect certain aspects of this. So one way to see this was, there was this paper by Patrick Hayden and Jeff Pennington, which talked about approximate error correction. So approximate error correction one could think of as sort of trying to do error correction in infinite dimensional Hilbert spaces. That's really where this issue shows up. And there were interesting effects that they found there. So maybe similar things also affect the result that we have obtained. So one should take this result with a pinch of salt in that sense. But okay. So with that, let me thank you for listening to me. Yeah.
Thanks. We have time for maybe one quick question. If anybody has something else they want to ask?
Any ideas how what kind of tensor network would be more appropriate? Like you're saying it's not simply so if I choose the tensor network where the tensors are perfect tensors in different alpha blocks with
Yes.
weights, you're saying that's also not enough, right? I mean, because so a single tensor network or a single perfect tensor network is still not completely. I mean, it's roughly like a single alpha block,
Yes.
but not.
Yeah, it's not so clear how to do this. I mean, it is a single alpha block, and so in some sense, the tensor network does more than what you asked it to do, because in holography, there's just no way to find this, or at least it's not clear from the semi-classical prescription. How do you exactly fix the areas of all of these subregions simultaneously? So, yeah, this is something I've still been thinking about. I don't have a good answer to this yet. But it would be an interesting thing to understand how exactly it's not even clear. I mean, tensor networks were toy models that we took for holography. So it's possible that it satisfies some features of holography, but maybe some features are absent. So it might be a feature of being a toy model, but it might also be something more interesting, wherein there's something about holography we can understand from understanding tensor networks. So yeah, that's all I can say.
Okay. Well, then let's thank the speaker again.
All right.
Thanks a lot.
All right. Thank you so much.